So the second long talk for today is by Felix, who's visiting from University of Bristol. And this is the second talk at DIAS in 2 days, so thanks for that, Felix.
Thanks.
And he's going to tell us about constraints and aperiodicity.
Okay, thank you. Hi, everyone. I'm kind of from a condensed matter background, but what I'll be talking about today is kind of rather mathematical, I suppose. But I see it as it's kind of building up field theories from microscopic models, which had a kind of condensed matter motivation, but they've sort of become a bit more abstract. So I'll give you the idea as to why we're interested in this topic, and I'll tell you the results we've found so far. I don't have an archive reference for you, but we're writing things up at the moment. So the talk is about dimer models. From a mathematical point of view, you can think of putting dominoes on a chessboard like this, and you can imagine all the different ways of doing that. You can try and count the different possibilities. I don't know if anyone knows how many ways there are to put dominoes on a chessboard. No, I ask this just in case anyone happens to know the number. So it's a maths problem, of course. You know, it's not just dominoes on a chessboard. It's really what we're doing is taking a graph. That graph is bipartite, meaning we can colour the vertices of the graph two different colours, so that one colour connects only to the other colour, or vice versa. Okay, so it's like blacks connect to whites and whites connect to blacks. The whites don't connect to whites. And then the dominoes are really edges on the graph, which connect nearest neighbours. Okay, so each one's going to cover one black and one white side. So we call these things dimers. In condensed matter physics, these came from, we think of, say, a two-dimensional crystal lattice, so going off to infinity, say, or very large. And we might have quantum spins sat on each sides. And then this model would be relevant when those spins form singlets. Okay, so the dimers here are indicating which spins have become entangled to form singlets. Shortly, I'll show you a quantum version of this where we allow superpositions of dimer placements. But there's a lot of intuition from the classical case, and a lot of the work is classical. So it's a hardcore constraint, meaning no two dimers can touch the same vertex, and there can be no vertex that lacks a dimer, although we will introduce those in a second. So if we do take a dimer out, so remove it, we get what we call a monomer. And so that's the two sites that were covered up by the dimer become revealed. From a physics point of view, you can think of, so originally these were diatomic molecules landing on a crystal. Now, as I say, it covers a lot more things, and in particular, we think of it maybe being tangled pairs in the crystal. But if you're thinking of the original diatomic molecule thing, then these are just revealed atoms that were on the surface before. But you can consider other, once I've created them, say that costs me some energy, I'd like to cover them all up. But once I've put in the energy to create a pair, I can move them around by rearranging the dimers or dominoes that are there. Okay, so if I colour this one green to show that it's moved, I can think of these monomers as hopping around. It hops by jumping across one unoccupied, then one occupied edge. And if I can get them back next to each other, I can annihilate them again, cover them up with the dimer. And you see that I've switched from one of my dimer coverings to a different one in that process. So we call any of these things a perfect dimer match. So that's a graph property. We're taking the graph and we match every vertex with one of its nearest neighbors. And so it's switched from one perfect matching to a different perfect matching by creating a pair of monomers and hopping them around and getting rid of them again. So you can think of this a bit like when you have a perfect matching, it's a bit like the vacuum or the vacuum space. There's no particles in it, but you can see there's a lot of inequivalent vacuums. And when you take a dimer out, you create a particle-antiparticle pair, and you can have them run around, and they've got colors which are going to correspond to charges. If I can get any black next to any white, I can always put a dimer back on and get rid of them again. So in the classical problem, that's the kind of sort of neat analogy, but that's all. When we make a quantum version of this, there's a really precise sense in which those do behave like particles. And we can ask about properties such as confinement. Can we separate them to infinite distance at finite energy cost? or does the energy of separation grow proportionally to the separation of quarks? We can ask those sorts of questions in this case. Okay, so the answer to the question earlier is not at all obvious, but there's a very nice theorem by Castellane which lets you count the number of perfect diamond matchings in any planar graph. And in particular, if the graph is periodic like this, you can get a nice closed form solution. I think the answer is, it's about 13 million is the answer, the number of ways to put dominoes on a chessboard. Okay, so the quantum version looks like this. It's worth talking you through it a little bit. Let's get a picture of the diamond matching up again. So the interest of physicists, it's been of interest for decades, but in the 80s it was made into a quantum version. And the original motivation was to try and match a certain theory of high temperature superconductivity, something called the resonating valence bond state. So this Hamiltonian was written down to give the resonating valence bond state as an exact ground state by construction. So let me talk you through it. This term in Hamiltonian is a potential term. This is kind of classical. And all it does is it counts the number of squares, in general we term these as plaquettes, that have dimers on opposite edges, either vertical or horizontal. Okay, it just counts up the number of those things. And we call these flippable plaquettes, like this one. They're called flippable because if I have this, I can always take the two dimers and switch the positions, and that's also a legitimate perfect match. Doesn't change anything else. So this term is kind of classical. It just counts the number of flippable plaquettes. This term over here is a quantum exchange term. So this actually enacts the flip, but in general, it allows you to create quantum superpositions of diamond placements. Okay. So it's a neat mathematical model you can write down. It was originally physically motivated by high temperature superconductors. We now know it can't really correspond to that, but it does lead to all sorts of physically interesting models, in particular quantum spin liquids, where it is still kind of relevant model. So something I'll be talking about in this talk is a really neat mathematical mapping for these things. I've shown you a classical picture of diamond placements again. There's a neat mapping called a height mapping. So what we can do is label the faces of this graph, the squares, with integers. So I'm going to pick a random one to be height 0. I'm going to call these integers heights. And then I'm going to work clockwise around this vertex and increase my number by 1. So I go 1, 2, 3. So the number's increasing by 1 as I cross an edge in clockwise direction around that vertex, unless there's a diamond there, and then the number drops by 3. Okay? So that's just a rule I'm going to define. We call these integers heights for a reason I'll show you in a second. On the neighboring vertex, I want to go in the opposite direction. So I want to wind anti-clockwise around this vertex. Why does it go clockwise in this one, anti-clockwise here? Well, the graph is bipartite, so I just keep track of which bipartite vertex type I have, if it's black or white, and I wind in the opposite direction. And then you see that my set of dimer placements is in one-to-one correspondence with my set of integer heights once I've picked an initial height. Okay? So this is called a height mapping. I find it really neat. So if you give me the integers, I can tell you where the dimers are and vice versa. It's called a height mapping. For this reason, you can think of these as heights coming out of the 2D plane. So this is a picture of those heights there. I kind of turn it on its side. You see it goes like 1, 2, 1 across that edge. Okay? So it's at this point, it's still kind of exact. This is still in one-to-one correspondence with the dimer placements. But the neat thing now is that you can systematically coarse grain these heights. You can average over these height positions, and you form then a smoothly varying field, which is no longer integers, it's now some real valued field. And this is quite a systematic way to go from a microscopic model to a field. In this case, classical, but we can also do the quantum version. Then we go to a quantum field. So it's like a nice playground for looking at some of the physics of field theories and how they emerge from microscopic models in like a nicely some parts of the model are exactly solvable. It's not in general, but let me tell you about where it's solvable now. Yeah, so in particular, when we form this smoothly varying height field, where h is now some real number, you can show that in the square lattice, at least classically, you get this coarse-grained action. So you have a term here that's, so if we didn't have this term here, your solution would be what's called a Gaussian free field. It's like a higher dimensional version of Brown's motion. This term here is favoring locking into the lattice with periodically varying heights. Okay, so this is kind of saying, depending on your lattice and interactions that you have between your dimers, you might want to have something that's just varying as something like Brownian motion in 2D, or you might want to take account of the microscopic lattice structure and lock into something that knows about the lattice itself. When we make the quantum version, you get something like this. I've actually skipped one term, but there are quite neat arguments to get to this. This is fairly robust, like it's very believable. This is the action you always get. There's a simple RG argument that gets you fit. This is slightly more hand-waving, but still, it's fairly rigorous in the scheme of things. And there's then this nice mapping to something that looks very much like 2+1 dimensional quantum electrodynamics. In fact, it's what's called compact QED. The compactness turns out to be important in a second, but basically it's very much like QED, except that your V is coming from a term with a cosine in, so your heights have to be equivalent to a height once you've increased it by integer 4. So it's kind of a technicality, but it turns out to be quite important later on. So if I come back to the Rockstar-Kittleson model, or the quantum dimer model, they wrote it down so that it has an exactly solvable point. So it's not solvable across its whole phase diagram, but at V/T = 1, this thing can be exactly solved by construction. So I set V equals T, it's possible to write down the exact quantum many-body ground state. And it's given by an equally weighted superposition of all possible classical perfect matchings. Okay, so it's a really neat model for this reason. If I can understand what all the different dimer arrangements are classically, then all I do is just superpose them with equal weight, and I get the full quantum many-body solution. Okay, which you don't typically expect to get for models, right? So at V/T = 1, you can solve it exactly. In the rest of the phase diagram is a bit trickier, but there are some places we can talk about. So if we go into V/T is -infinity, then we're kind of forgetting about the T term, and we're saying that V is very large and negative, so we really want to have dimers aligned on opposite sides of the plaquette. Okay? And this is one of the best ways we can do it. So in this case, we've got half the squares are flippable, the other half are not. That's the best you can do. There's 4 different ways to do that. I can do this one, I can rotate 90 degrees, or I can shift over by the side. So in condensed matter language, we've undergone spontaneous symmetry breaking. We've selected one of 4 ground states. And when I look at these particle excitations, these monomers, and then the opposite limit, you can do the same thing. This is also, so these 2 end limits are really classical. At this point, we can also solve this quantum mechanical. In this limit, we really don't want flippable plaquettes. So one of your options looks like this. It's called a staggered state. Okay, so none of the squares are flippable here. And again, there's 4 symmetry broken states you can choose from to do that. And the one in the middle we call the RVB state, or the resonating valence bond state, and that's how the model was written down to give you that. Okay. If we look at either end, at the classical models, you can see that your monomers must be confined, and you can see it through a really simple argument. I create a pair of monomers. Okay, they're blue and red now rather than black and white. Same difference. I can hop them apart, just like before, like this. Each monomer hops by going across one unoccupied edge, and I shift the dimer over. But you see that for every hop apart they take, I violate my condition of having my flippable plaquettes. You see, it costs me like 2 flippable plaquettes for every hop they take. And that's 2 units of V, so you can see that the energy of the monomer-antimonomer pair is proportional to their separation. Okay, and so this is exactly what you get in quantum chromodynamics, what we believe you get with quarks. You only find quarks in 2s and 3s, you never find them by themselves. So for the same argument, when you go to the quantum picture, if you try and separate 2 quarks, their energy is proportional to their separation. It'll always cost you so much energy to separate them that you'll create a new quark-antiquark pair and you always find them bound up. So we say those are confined. The same argument holds in the staggered state. You can hop them apart just like before, but for every time you hop them apart, this time you introduce flippable plaquettes, and those cost you energy again, so same argument. At the exactly solvable point, call this the Roxar-Kibbleston point, the V over T equals 1, it turns out that you can show, also quite straightforwardly, that the particles are deconfined. Okay, so in that case, you can separate them off to infinity at finite energy cost. Good. So what about the rest of the phase diagram? We understand this on this side. Okay, there's some subtlety around here. I'll show you in the next slide. Over here, it's argued about even numerically. So it's a very simple model, but even with numerics, people argue about the precise forms of the ground states, and whether there are phase transitions and things. One thing that's basically universally agreed upon is that this deconfined point is only a single point in the phase diagram that's deconfined. So you might have thought the particles, okay, you separate them to infinity at finite cost. If I change my V over T slightly, is that still true? And it seems that it's not. This is what's called a deconfined quantum critical form. So it's a type of phase transition between long-range ordered states. So this is believed. The argument for it is at the emergent level. So this is all kind of microscopic stuff. But when you coarse grain out and look at the quantum field theory, there's a theorem that is kind of invoked here to explain this by Polyakov, who says that you cannot have deconfined phases in compact 2 + 1 dimensional U1 gauge theories. There's a lot going on in that statement. The key bit is that the emergent field theory you get out of this compact QED3, is an example of such a field theory. And so at the coarse grained level, it seems to be the case that you can't have a whole phase that's deconfined here. You can have deconfined points, but they must be isolated points in phase diagrams. So you don't need to understand where the statement comes from, but it's widely accepted. I think these days it's actually quite formally proven. But it's at the emergent level, not the microscopic. So we've been wanting to understand this statement. One reason to think that, not necessarily to question it, but and then confinement is related to periodicity. That's the thing I was showing before. In these two cases where I show you can write down the exact ground states, you see that the reason the monomers are confined is because the dimers have this periodic order. Okay. Is that kind of clear? It's because, let's take the London state, for example. Because the dimers want to line up like this everywhere, if I create a pair of monomers and hop them apart, I violate my lining up condition. Right? Because they're all ordered in the same way, then I've got to change that to allow the monomers to hop, because monomer hopping corresponds to shifting a dimer that was already in the position it liked the most. So you can see that it's always going to cost you, your separation will always be linear in energy whenever you have periodic dimer order. Okay, this is kind of the motivating idea behind the rest of the talk, so let me know if that argument isn't clear. So at these points I can show you what the ground states are and give you the argument. At the other points, because of this Polyakov's theorem, it's widely accepted that you have long-range order everywhere else except for this point. So whenever you have long-range order, the form it takes we're not sure about, plaquette order or something, some quantum things going on, but it is some kind of long-range order. Okay, and so therefore you're always going to have confined particles away from that point. So one result that actually two results that called this into question led to this idea of Cantor deconfinement. It's very cool. It's a cool name, and I think it's a really nice result from 2004. They argued that this is the phase diagram I was showing you before with some extra bits in it. If we look on this side, where we're heading towards the staggered state, the microscopic understanding is that this staggered state is the ground state all the way across the phase diagram right down to the arcade. It's a bit of a mysterious, well, not mysterious, it's quite a strange state in the sense that it's kind of disconnected from the others. If I think of my local moves as those flip moves, there's no way to apply a flip to this because there's no flippable plaquette, so it's kind of isolated. It's in its own topological sector. But this paper was saying, actually, if you again look at the field theory level and you add generic perturbations away from that RK point at the field theory level, this paper and another paper at the same time argued that actually there's something a bit more interesting going on in this region. And if you look at the heights that I wrote down before, of those integer mappings, that, and then you call Spectre your height field. When you look at the staggered state, if you write down those heights, you'll find that the heights form a smooth slope that just winds up as fast as it possibly can in one direction. And there are 4 directions to do this on the torus, so there's 4 staggered states. On this side, by the way, all of these are flat heights. Okay, so we go from flat, and then it was believed you jump up straight to maximum tilt, as it's called. But in these papers, they're arguing that actually there's an interval here where whenever the tilt is an irrational number, you have deconfinement. And whenever it's a rational number, you have confinement. Okay? So this is the claim. Nobody's ever been able to come up with a microscopic picture as to how that works. Here's a sort of cartoon of it. Yeah.
Tilt.
So again, so we have the heights equivalent to the diamond placements. And in the staggered state, the heights wind up like this. And so the height field tilts as fast as it possibly can. So literally, just like if you write down the heights, it will go like 1, 2, 3, 4, like that, and just go up. So that's called a tilt.
So it's just a number between what and what?
Well, that's a good question. Because if you try and make it microscopically, if I have like n sites or n squares in the system, then it would have to be like the tilt would have to be somewhere between 0 and n, right? It would be minus n. But they're arguing that if you work entirely at the field theory level, where you've lost information about your lattice, it's smooth, then somehow you can have tilts that are irrational numbers. Like this is what I'm saying. Like microscopically, you can't even conceive of a way to do that, but at the field theory level, you can. So whenever you get a rational number for your tilt, you get confinement. And whenever you get an irrational number, you get.
Yeah, I understand what you're saying. So if you had a quantum partition function,
yeah,
how would that happen? How would that feed in?
Like how would it come about, sort of microscopically,
or even emergently? I mean, how would you understand that?
So the way they do it in this paper, they write down the quantum field theory I wrote down before, the quantum action, so the partition function. Then they add what they argue are generic perturbations away from that. It's like small perturbations taking you off that point. So changing the action and adding like the next order of terms. And then looking at that, they argue that if you take a look at that new field theory, you'll find that whenever there's an irrational value of this tilt, then you find you get t.
And this is a finite sum that we're doing. Have they taken the limit?
Yeah, well, exactly. That's the thing. Like they're always, it only works into the limit. Or like they're arguing there should be a way to manifest this microscopically, and that should be the limit of some microscopic model. But they only work at the level of the field. And in the sort of 20 years since this was worked out, nobody's ever come up with a microscopic version of this. And in a sense, it's very hard to try. They tried, yeah. Yeah, in fact, Fradkin wrote a paper about a year or two after this, sort of claiming how well it wasn't apprehensive to this. And in a sense, like, how could you possibly do it, right? Because the way you would typically take your thermodynamic limit is to take some kind of finite size system, all of which will have to have rational tilts. And you can keep increasing the size of the system and, make a better and better rational approximation to an irrational tilt. But the irrational can only come in when you get the.
It's kind of different only if you cannot have anything if you have an irrational tilt.
Sorry, you can't.
So what does it say to get about irrational tilts?
So at the field theory level, if you have an irrational value of tilt in the whole system, then you have deconfined onwards.
Yeah.
So the tilt is the coefficient you have in this cosine. What is the tilt?
No, not quite. It's perhaps I should have shown a picture of it. I'll draw you a picture now. So if we take our lattice like this. Sorry, so if I draw you this, and I'll put a staggered state on there, which will look like this. And then I put my integers in here. So I'll have 0 here, 1, 2, 3, and 1, 2, 3 like this. Then this one goes 2, 3, 4, 5, 4, 5, 6, 7, 6, 7, 8, 9, and so on. And so you see my height integers are just winding up as fast as possible in that direction. So this is what would be called a tilt, and it's tilting upwards that way. So it's like a slope heading up uniformly.
Yeah, but you know, you're saying that they're looking at the field theory.
Yes, that's right.
So the field theory is given with the integral of some expression with a cosine, as far as I understood.
Yeah, well, and so
where do you see now?
So the tilt
they're not looking at the lattice, they're looking at the field theory.
Yeah, so it would be in the solution for the height itself. So when you look at the solution to that field theory, bear in mind I've missed a term expression, but you're finding solutions to the height field itself, and you're finding that that height field is now trying to form a slope. Okay, so it's just increasing, say, in the y direction in this picture. This one's microscopic, but when I coarse grain, it'll do some smooth, real valued field, and I can just make a function that's going to go straight. The action only cares about the height modulo.
The ground state of this Hamiltonian?
Yeah, exactly. Yeah.
So you're just looking at 0 temperature for this Hamiltonian.
In the quantum case, they're looking at 0 temperature, yeah. When you take the equally weighted superposition of classical states, those are essentially the infinite temperature classical cases that you superpose to get the 0 temperature quantum case. And exactly, then as you tune your V over T, which is sort of embedded in this action, then if you put it in the right regime, you expect to get these maximal tilt states. What they're arguing is, if you look at the field theory, then it seems there's this sort of somewhat mysterious region, which they call Cantor deconfinement, where you actually have irrational tilts, and then you get the yeah.
And so in that regime there, it's because, so is it that they add an additional perturbation term to the action, or is it more that we statistically solve H, it becomes irrational? That's what.
They add additional terms to the action.
And is there a simple part of the additional term that they add?
Is there a
simple expression for the additional term that they add?
No, even to be honest, even the action I skipped one of the trickier terms, but yeah, the generic perturbations are kind of, they're not obvious, but they argue that they're the lowest order.
They're less than ugly.
They're quite complicated. Yeah.
In going from the microscopic theory to the field theory,
yeah,
it would be natural to choose a larger unit cell.
Mm-hmm.
You have just chosen the minimal unit cell there, which had involved 2 plaquettes. You could have increased, you could have added a slightly larger terms which involved 4 plaquettes of different parameters, which would mock up at different weights on the
yeah, I think that's right.
Larger unit cell, and that would be very natural because you wouldn't see that in the field theory lens.
Yeah, I think that's probably right.
So they haven't tried something like that? Because I can see how you get different heights, different potential values for the heights.
I think that might be factored into the, so even when you make it classically, you can have 2 pi p times h here, where p is some other integers. And in general, the action you'll get will have a sum over all possible p's. And those are going to correspond to higher order terms that provide large unit cells. But this is where you have a renormalization group argument, which shows you that they're always irrelevant compared to this term. It's always the most relevant of those terms. So you might be right that the right thing to do is to include those terms still and redo the argument. What I can do is report what they've said about this in the earlier papers. So, I mean, anyway, so it's a very interesting claim. As I say, I think people are skeptical of it for the reasons that people are saying now. Plus, no one's really come up with a way to systematically get from the microscopic model to find these things. So you could well say, well, this is just like a quirk of having only worked in the continuum limit, and then you get irrational numbers, and they don't really have any physical meaning. I think that's kind of that could be a reasonable claim. Still, it was kind of motivation for us. We don't end up using this, but it's something we've been thinking about. So what we've been doing in the last few years is to say, okay, the confinement properties microscopically, we can understand that when we have periodic placements of dimers, then we always get confinement. And You can have deconfinement at the RK point because you have an equally weighted superposition of every classical perfect matching. And so you don't have any periodicity, you've got everything. So it's in a sense like disordered. So what happens if we take something that's not a lattice, that doesn't have periodicity itself? Then you can't have periodic placements for dimers. So perhaps you can change the size, or perhaps we can find like a deconfined phase in there, like microscopically. So we were thinking either we might find a way around Polyakot's result, or we might find a microscopic version of what's going on here. Now, we didn't do either of those things, but that was the motivation. Okay, I'll tell you what we did find. We found some interesting stuff, but it was what we set out to find. So what we were looking at, the obvious thing to us to look at was quasi-crystals, or like aperiodic tilings. So we started with the Penrose tiling, then we did the Ammann Beenker tiling, and then more recently the Spectre. Actually, this has a reference now, which is better. So the idea is we have, well, the way I used to say this was you have two different types of unit cell which fit together to create a pattern that has no gaps or defects and goes off to infinity, but it has no periodicity. So it's long-range ordered, but not periodic long-range ordered. In fact, they have a discrete scale invariance to them instead of a discrete translational symmetry. So then we can try and put dimers on these things, and you can't get periodic dimer placements. So can we get around this, or can we find some deconfined phase was our motivation? So I'll talk you through the results we've got over the years, and tell you where we're going with it now. So we started with the Penrose tiling. And here are the results from 5 years ago now. So first, it should be noted that the Penrose tiling is bipartite. In fact, so this bipartiteness of being able to colour the vertices blue and red, say, so blues only connect to reds and vice versa. That's equivalent to the statement that all cycles on the graph are of even length. And since it's made of rhombuses, that's always true. Okay, so I can colour the vertices those two colours. What we found is that you can't have perfect matchings of Penrose tilings. So there's a minimum density of monomers that must exist. Because of the long-range order, you can actually prove exact results, even though there's no periodicity. So we found that the minimum density of these monomers is exactly 81 minus 50 times the golden ratio, which is about 10%. The way you show this, by the way, so what I've shown here, these are some dimers, purple edges, blues and reds are the monomers that have to exist, but they don't have to exist in those places. They can move around, they can pop as usual. But what we're able to prove is that these thick black edges here can never have a dimer on them. You can prove that if you put a dimer on one of those edges, you can't imply the existence of a pair of monomers that can annihilate across that edge. So these edges never get dimers on them, so you might as well take them out of the problem. They don't contribute to the matching problem. And if you take them out, your graph disconnects. For example, this region in here just has one red site that can hop around, it's got no blues to annihilate. Okay? So this is how you end up proving that. Okay, so it's a kind of cool result, but it wasn't what we were looking for. It wasn't our original motivation. In fact, you always get confinement for a kind of trivial reason. It's set by the average particle spacing. So I can create a blue-red pair in the red region, say, but I get a correlation that's set by the mean spacing of these particles. It's sort of understood. So that didn't work out. So our next attempt, oh, I'm sorry, just to make it a bit more physically motivated, actually. This number, 81 minus 50 times the golden ratio, it sounds like a crazy number to get out of something. But with hindsight, and we didn't know this at the time we published the paper, the number had appeared twice before in the context of Penrose tilings. So one was in tight binding models, where you have electrons hopping between nearest and neighbor sites. And it had been conjectured that there's a density of zero energy modes. A band with some density that sits at zero energy, it's flat. And it was conjectured that the density of that thing was 81 minus 50 times the golden ratio. Then more recently, there was a study of the Hubbard model, so kind of closely related. They saw these sorts of structures appearing. There's a weird kind of antiferromagnetism that comes out. And they again conjectured that same number, essentially related to the earlier one. And so with hindsight, we've proven these conjectures, but we actually didn't know about them at the time. So there's a reason for this. There's a known that the counting of these monomers is known to relate to the counting of zero modes. So there was actually we could have known that if we'd have known about these results. Okay, so this is physicists like flat bands in these things, so it's handy that these calculations tell you about them. Okay, so our second attempt was the Ammann Beenker tiling. So very similar to the Penrose tiling, but with different tile types. So it looks something like this. And in this case, I had a really talented summer student, Jerome Lloyd, who's now finishing up his PhD in Geneva, who proved that you can perfectly match the Ammann Beenker type. So this seemed a lot more promising. Okay, so you can color the edges so that every vertex meets exactly one colored edge. You don't need monomers here. So we get around the problem in the Penrose tiling. What do we find for our statistics? Well, it was pretty surprising, to be honest. If we look at, so these are our correlation functions. If we sit, so this is what's called the monomer correlation function. So we take out two sites from the graph, and then we count the number of perfect matchings that remain when those two sites remain. Okay, and you typically expect that to decay either as a power law, as a separator, or as an exponential. And then confinement can be identified from what value they tend to at infinity. So if your monomer correlations tend to a finite value, then that corresponds to confinement. But what we found was that the monomers don't care about each other at all. They care about the structure of the graph. So it was very surprising. Yes, this monomer here, it has some partner, but it doesn't care where it is. It cares much more about features of the graph, as you can see here. So it knows about the center of this region. You can see these like eightfold regions that are doing. Same with the dimer correlations shown over here. So I can say, fix this dimer in this position. How many configurations are there with this dimer in this position? So, and again, typically you expect those to decay with distance, but in this case, they care a lot more about the structure of the graph than they do about the dimers themselves.
So how do you count that? There's huge numbers.
Yeah, so well, there's a very efficient algorithm for doing it on planar graphs, this so-called FKT algorithm. So basically, you form a big determinant and then take a determinant to the graph. So that was Castelling's result, basically, and yeah, that's why we're able to do any of this stuff, basically. Good. Yeah, and plus the talented summer student who wrote all the code. Okay, so it was so I haven't actually shown the plot. So actually, again, in a sense, these things we termed anti-confined. It was really surprising, but actually, if you create a red-blue pair of monomers, they actually kind of want to accelerate apart. But that's because they don't really care about each other at all. They care a lot more about the graph. And there's a kind of simple argument as to why they're attracted to some sites and repelled from others. It ends up being a very glassy problem. Those sets of edges I showed you in the Penrose tiling that can never have a dimer on them in any perfect matching. In the Ammann Beenker tiling, you get something very similar. It's a closed set of edges, but it must have exactly one dimer on it. It doesn't matter where it goes. So basically, you take this monomer, those sets of edges have to match the graph symmetry, so it's the graph property. They enclose centers of eightfold symmetry. And if the center is kind of larger, it has more of those things nested around it. And so you can kind of think of the monomer taking a random walk. It can cross through one of these things in one direction, but to head back out again, it either has to retrace its steps or find that one diamond that lies at the end. So basically, they kind of get trapped. They head in and they can walk in wherever they like, but then they get trapped. So eventually, they'll walk in through another one, and they get kind of attracted to these centers of eightfold symmetry.
So just to kind of to understand how you computed here, the monomer, you were saying you just took the Castelling matrix for the graph, deleted the vertices where the monomers are, and recomputed the determinant.
That's right, yeah. Actually, I think we had to remove the central site in some of the calculations as well, but yes, that's essentially it. Yeah, we had to take the central site out because otherwise you've got like A10 plus 1 vertices, so you have no perfect matchings. So you take the central one out, then you have A10, you have a perfect matching of that. Now you take out a pair of other sites. So typically you take out a dimer and you do like a random walk of the monomers and let them end up somewhere.
I'm confused as to why you have to take the central.
You just have to take one out.
Now you won't have an even number of vertices if you take 3 out.
Yeah, you will, because it's quite eightfold symmetry, but it has one at the center. So it has A10 plus 1 in the whole region.
So there's one at the center, which just makes it. It's not
Yeah, so
the central one is not bipartite.
Yeah, you've just got to take one. It's bipartite still, but it has an odd number of vertices in the way we generated it.
Obviously,
So there's a natural eightfold symmetry, and it makes sense to keep that for a boundary condition, but then you've got 1%. So we just took that one out. That doesn't affect things too much. Okay, so again, we can't really say about this confinement or deconfinement, unfortunately. It cares more about the graph in this case. So then, 2 years ago now, my earlier claim that you need 2 different unit cell types to make these infinite aperiodic long-range ordered patterns was disproven. Actually, so the story was very nice. There's a guy called Dave Smith, who's not an academic. He just likes to cut out shapes out of card and try and fit them together and see if he can tile the infinite plane aperiodically. And it's a task mathematicians have been trying to do for decades at least. And we failed. I've been trying to do this as well, but Dave Smith managed to do it.
was he aware of Penrose tilings?
Oh yeah, he knew about Penrose tilings. But yeah, so I asked him how he wants to, like, I said, so, you know, do you like doing jigsaw puzzles or something? He said, no, I hate jigsaw puzzles. I just like trying to make tiles that tile the plane only aperiodically, of which there were no examples. So it's good he found one, and in fact he found an infinite number of them as well. So then he contacted these people, so like Ivan Strauss is a well-known tiling expert, and they sort of helped him formalize a proof of it. But he found the shape by himself, and it's actually very simple. So this one needs a tiny modification. You need to put like a little bend in the edges to force aperiodicity. But the idea is that there's only one tile type here. It's colored differently, but they're all identical. Okay, and with this like little modification of the edges, then this thing will tile to infinity, but only aperiodic. Okay, so it's very cool. It was a very exciting result. We had a whole conference to celebrate it. Good. So we thought, well, we've got all this machinery. Let's give it a go on this. And the result turned out to be really remarkable in this case. So we can define our quantum diamond model like before. So this is just supposed to be the generalization of the thing with squares. So this is maybe the diamonds on the top end, bottom edge of the square, and this is like the diamonds on the side edge. Right, you flip this one to this one by shifting the diamonds around once on the. Okay. Otherwise, it all works the same. So if this were your whole tiling, just a single tile, you can form the symmetric and anti-symmetric combinations of these, and in this case, the symmetric combination would be your ground state at your depending on your V and T. Okay, so then if we look at what happens in the real tiling, obviously on the tree of finite patch, classically. We proved again that all your perfect matchings take this form. So it perfectly matches again, like the Ammann Beenker tiling. But this time, the purple edges must appear in those positions. Those diamonds are completely fixed. And similarly, these white edges cannot have diamonds on them in any perfect matching. Okay? We can prove this using this discrete scaling variant structure. The only degrees of freedom that are left are on each of these darker tiles, where I can choose either the blue edges or the red edges on that tile. We can do that independently for each of those tiles. Okay, so I end up with 2 to the n degrees of 2 to the n independent perfect matchings. 2 to the n plus 1, which is the boundary, also free to choose.
So you can't form a tree. You can't form a cluster of 3 or more. You've only shown us clusters of 2 pairs of tiles.
Clusters of 2? Oh, what? You mean these, the coloured in ones?
Yes.
Yeah, so don't worry about the colouring. That was kind of taken from the original paper. Like out of interest, the tiles are all identical, but if you're into tiling theory, like this dark one, all the other ones, except for the dark ones, appear 30 degrees rotated from each other, whereas the dark ones appear 15 degrees rotated from the others.
Why come in the dark ones?
So it's like, yeah, I believe you, this is black. That's a good point. I think of this as colourless because I made it on my lithographic thing. I put that see-through. That's yeah, okay. The dark green, that's it. Okay.
But can I put 3 of those darker ones together?
No, that's the thing. So there is some, like this comes out of the structure of the tiling. It is the same tile everywhere, but there is some sense in which these are a bit different from the other ones because of this 15-degree rotation business. And you see that they have a spacing away from each other, and that turns out to be important for us. So
I don't understand the 15-degree one. You said that again.
Yeah, so let's see an example of one. So if I find maybe its head like this, coming out like that, then that thing will be 15 degrees rotated from another one like this. Oh yeah, this one here.
Yeah, okay.
Whereas this one, compared to anything that's not that color, will only be rotated through 30 degrees, some multiple of 30.
Well, that's fine. It's still the same time.
It's still the same time. Some tiling people, who you might argue were a bit upset they didn't come up with the tiling, consider that to be, in some sense, a bit different. But I think no. Yeah, but the authors coloured them differently, and it turns out there is significance to that set of things they happen to colour darker. Okay, so out of interest, the way you actually build these things is you take your tile, you form two different cluster types, which are called meta tiles, and then those cluster types sort of form the two tiles that are like the Penrose tiling, and those things are going to fit together in the aperiodic pattern.
So how many vertices do these things have? An even number?
That's a good question. We've defined them to have an even number. There is some subtlety about that point. Let me find it. So there are some cases where the number of vertices depends on how the tiles meet the other tiles. Here, for example. So you see, we've defined a vertex in the middle here, which is very natural because that same tile elsewhere will have a meeting point there. Like here, for example. So here it meets another one, but here they've gone back to back so that it doesn't meet it. So you can either say there's a vertex there or not. If you say there is a vertex there, they will have 14 vertices in this pattern. So I guess that's a matter of convention, but if you stick the wobbles on to make them fit, one of the ways to do that is to include a two-valent vertex. Yeah, since we need to bipartite graphs, we needed that.
And if you're building them from the same structure everywhere.
Yeah, exactly. Yeah. Anyway, that's what we did. So if that's the case, then your classical perfect matchings take this form. And then the really remarkable thing is that so you get an exact solution to the classical diamond model, right? Because an exact solution is finding the partition function, from which I can calculate anything else. My partition function is just counting the number of perfect matchings. And I see it's just 2 to the power of the number of these things, plus 1 to the boundary. But then the really remarkable thing is that I can also get the exact solution to the quantum diamond model.
Just to check, is the boundary frozen?
No, there's a degree of freedom on the boundary.
You can rotate the boundary.
Yeah, whenever you see these blue-red patterns, that means you can choose either blue or red independently.
Is that all?
Sorry?
Is that all?
Yeah, there's just the one on the boundary. And really, we're working in the infinite limits. There isn't a boundary.
So partition functions is very simple.
It's really simple, yeah. Yeah, it's really remarkable. Yeah, the problem reduces in the end to just having totally independent tiles, but that came out of the combination of the strength of the dimer constraint combining the graph connectivity. We haven't understood the general rules for what gives this, and I've never seen it anywhere else. Yeah, if you try and build a graph that has that property, that it has like isolated bits that have dimer freedom and everything else is fixed, we've been incapable of doing that.
So you're going to give this guy a job then?
He doesn't seem to want one. He came to the conference. He was worried about coming because he said he'd be surrounded by all these clever people and he'd be scared. And we were like, well, they're all there to see you. Roger Penrose had been emailing him, was really keen to talk to him. Yeah, it was really nice. He was a really nice guy. Okay, so we've got the exact solutions to the classical problem, but then really remarkably, we have the exact solutions to the quantum diamond model in this case, because it's so simple. So the ground state is just take the symmetric combination of blue and red on every one of these things separately. And not only do you get the exact solution to the ground state, you get the exact solution to all the excited states as well, because you just switch the symmetric to the anti-symmetric combination on any of them independently, and it'll give you all your excited states. And it works across the whole phase diagram. So this, I think, you can't exactly solve the quantum diamond model on the square lattice. In fact, people argue about it even numerically. They can't even agree on what the ground states are. But here you can exactly solve the whole thing across the whole phase diagram. And what we're looking for is that the particles deconfined everywhere. So if you create a monomer anti-monomer pair, you can run them off to the boundaries or if it's infinitely big, running to infinity at zero energy cost. You don't create or destroy flippable plaquettes in doing that. So it doesn't cost you anything. Sorry?
They're free.
They're free, yeah, totally free. And that would seem to contradict the statement, right? That's the thing we were trying to do, going against this Polyakov's theorem and saying, well, can we have a deconfined phase? I would say this is a deconfined phase across the whole phase diagram being deconfined. Unfortunately, we didn't convince one of the referees at PRL about this. They argued that, well, your states take exactly the same form at all points in the phase diagram, so it's not really a phase diagram. And I do take their point there. So as I vary d over t, like my eigenenergies change, but in a somewhat trivial way, my eigenstates are always the same. So they say, well, in that sense, it's not really a phase diagram. You need something to be changing. So I guess by analogy, if I want to help the referee out even more, I could take some model where I've got a solution as a point, and then I could just take some totally unrelated thing that's not coupled to it at all and tune some parameter in this one. And that thing wouldn't be a phase diagram, of course, even though this thing's taking different values over here. But our argument was, well, that's not really a fair comparison. If we'd have constructed this thing to have this property, maybe, but this has come out naturally through this combination of constraints and the graph activity. So I think it's rather different. It's come about naturally. So for example, if we consider the broader class of models, I would expect this to maintain this property. In particular, if we start allowing finite densities of monomers, that's a much harder problem, but potentially we might be able to still argue about this confinement deconfinement. Still, there would have to be ongoing work. This is where we've got to. However, yes, please.
In this case, you have this kind of disconnection with the kind of islands.
Yeah.
And so when you make the monomer excitation, let's say, to the island, is it that the monomers can only freely travel to the couple region, or they can also travel to other?
No, they can. I think we worked this out in detail at the paper. I create one there. So I can get to here. I think if I get to here, it just runs around and comes back out. Yeah, and then causes that one to have flipped. So I can find routes to get into infinity. Otherwise, they can run on to go if they like. They just have to retrace their steps until they get to a branch. And
okay, so they don't completely need to kind of avoid basically the islands kind of.
Yeah, exactly. You don't have to, but if you want to get them to infinity, yeah, you have to avoid them. Okay, so it seems like we've got around that Polyakov's theorem, but actually we haven't, because there's no height description for this, or at least we've never been able to come up with one. So remember, you want to write integers on plaquettes in such a way that when you wind around, you have this consistent change in these integers. And from that, you course grain those, then you get your field theory of that one. But we can't do that here, even microscopically. And the problem is that we have different valences of vertex here. So if you have, for example, somewhere there's 3 edges coming in and somewhere there are 4, so this situation comes about. Then, for example, if I have my dimer on the middle, if I wind around this vertex, I want to go 0, 1, 2, and I require the drop across here to be 2. If I go this way, I go 0, 1, 2, and I find this one's 3, and then the drop needs to be 3. And this doesn't work. I mean, this is inconsistent. Another way to think about this, the way you get this emergent fields theory, you get this compact quantum electrodynamics. There's a natural way to think of that, which is to think of a flow of current along edges. And then your dimer constraint says that if I have flow of 1 along each of these edges, then I have a flow of 2 out along that edge. But that only works if I have the same valence of vertex everywhere. If I don't, then I'm claiming that this one's got 2 flowing out, if I need it to be 3 flowing in. So there's a basic reason that that won't work. So you can't make height mappings when you have different valences of vertex. So this doesn't violate Polyakov's theorem. I thought maybe it did. How am I doing for time, by the way? Should we be sort of finishing out?
10 minutes, 5 minutes?
Okay, 10 sounds good. Okay. So from here, where we've gone is to say, okay, we've tried this all sorts of ways with fuzzy crystals. What we really want to do is work out the necessary and sufficient conditions for getting a perfect dimer matching that has a height description. So we don't want to make any assumptions about periodicity or anything else. So that's where we've gone from here. So we can call these things random graphs. In fact, we'll see they're not quite random. So here's an example of one of the things we're looking at. I'll put some dimers on it. So it emits a perfect dimer matching, and it emits a height description. So what we need, in fact, what we found is pretty simple. You need a bipartite graph, and it needs to have constant valence of vertex. It has to embed onto a surface. It doesn't need to be of any particular genus. So that's not really a constraint, because you can make any graph will embed onto a surface of sufficiently high genus. But the calculations get a lot harder once you increase the genus. So this one is embedded onto a sphere, for example. So the outer region is considered a tile as well. Okay? But typically we'll be working with toruses. If you're working on the sphere or the torus and you want a bipartite constant valence graph, valence is the number of edges coming out of each vertex, then you need to have a trivalent graph. That's what you can have. If you go to higher genus surfaces, you can have higher degree. So for now, we're just focusing on the 3-valent ones. And we found that actually there's a really neat argument to get to the field theory. So these arguments were made in the periodic cases, but they were phrased in the language of periodicity, like symmetry operations on the lattice and so on. But actually, if you have a bipartite graph, you've got an action that's a function of your height field. Bipartiteness, you can argue fairly easily, implies that your action must be invariant under side changes of the height. And having constant degree v means that the action should be invariant under shifts of v to your height field. Okay, I won't go through the details, but if you combine these two statements, it leads very naturally to that same action that you got for the classical diamond model in periodic graphs. So again, you need that renormalization group argument, but then you end up with this same action as before, the sine Gordon action. Okay, so this term is kind of being constrained here, you're getting these cosine type things, and height minus height gets rid of some other terms. So classically it leads to that, and then we believe the same argument will go through to get to the quantum case. All the arguments seem to be as they are in the periodic lattices. So it seems like whenever you're allowed to write down a height description of the diamond model, then you will actually always get the same results as in the periodic cases. That said, we can now address the question of confinement or deconfinement. And what we find, here's two examples of these things embedded on toruses. We find that the left one is confined and the right one is deconfined for monomers. Okay? And that's really surprising, I think, because they look potentially identical. The trick, the thing that differentiates them is that those same conditions imply the existence of a face 3 coloring. So I can color the faces 3 colors. So if the 2 faces share an edge, they don't share a color. Okay, you can prove that very easily. And if you look at the face 3 coloring you have here, the green faces are all squares, or distorted squares. So that turns out to be the key difference between the two. So here are our monomer statistics for larger regions. And here you see this one is confined because the statistics, this is a log linear scales, this is exponential decay. This is log logs, this is a power law decay. I say deconfined, it's critically confined, is another way to put it. It's the most deconfined you can have in 2 dimensions. Okay.
So can you say again what you did differently to get the, you showed us that when you colored them, there was a difference. So
Right.
Where did the difference enter in terms?
So do you see the difference between the two, right?
I can see the difference, yes, but I'm not sure how you made them different.
How do we generate them? We had to come up with our own algorithms for this. There are no
If you started and you decided that they were colored that way and you forced it.
No, we spotted this after the fact. We were like, how on earth is that one confined and that one not? We actually, our earliest algorithm generated things that do this. There's an easy way to make things like this. Then we realized that they were always confined. We thought that was the general rule, and then we were confused as to how the, say, the honeycomb isn't confined. We've disappeared. Yeah, but then we had to come up with a new algorithm basically to get the right hand one. So the left one's straightforward. You take any genus of surface, like a torus, say, you take a random walk on it, like this, and then so that'll give you a random graph on that surface, but it's not bipartite. But then when you have a crossing like this, you regularize it by breaking it apart like that, and then you have a somewhat random graph where it's 3-valent and it's bipartite. So that was our first algorithm, but you see it generates things that always have squares as one of your face colors. So then we realized that's a problem, so we had to come up with a new method to do this. That's how we okay. All right, so maybe I'll finish up because so this is a statement about your monomer correlation functions. I don't need to go into that in such detail. In fact, I'm just going to jump straight to this. I know we discussed this yesterday. I've thought about it a little more. I'm still happy with this, but we can chat about it afterwards. So, density of squares is dictating the emergent properties of the field theory level. Okay, so we're working with quantum dimers and non-classical dimers, but we're going to take the superposition of them into the temperature to get the exact solution of the RK point. Okay, it's the quantum dimer model. There are two cases that were known before that are periodic. We look at the honeycomb lattice, but importantly, we have this. We write down that either the quantum dimer model that I showed you before, or the classical bit, that's just the beta. Then, at infinite temperature, you have your monomer correlations look like this. They're a power law, so it's critically confined or orbitally confined. At zero temperature, in that classical case, you have the equivalent of the Columbian state. It looks a bit different, but it's a long-range ordered state, and in that case, you will get exponential monomer correlations. And there's a known transition between these two. It's a Kosterlitz-Thouless transition. Okay, along that line. If you go to the square octagon lattice, it's known that there is no phase transition. At zero temperature or infinite temperature, you always have these exponential monomer correlations. Okay, so those two cases were known. And what we found is that if we look at infinite temperature, where we can use this FKT algorithm, we find a phase transition. That was what the previous plot I skipped over was. We find there's a sort of diverging correlation length. We get phase transition at infinite temperature, which I think is quite cool. I've not seen examples of infinite temperature phase transitions before. You then superpose all those classical solutions to get a quantum solution, in which case this becomes a quantum phase transition at zero temperature. And so we can sketch what the phase diagram has to look like here. The reason density of squares is a sensible measure. Okay, maybe I'm going into too much detail here, but just say it before I finish. So the trick here with squares, my way of thinking about this now is that, okay, I'm going to put the thing on a torus. A torus is globally flat. And a globally flat tiling with a regular tiling would be a honeycomb in this case, if I want it to be 3-valent and bipartite. Okay, so it's, if I take hexagons and have 3 of them meet at a vertex, then that thing is going to be flat. Okay, that's a regular tiling of flat space. Okay, I do that often. We'll stick on a torus. Now, if I try and tile squares and have 3 of them meet at the vertex, of course that's not going to work because there's curvature there. That would fit on a sphere, but not on a torus. Right? If I take just 3 regular squares and try and fit them together, then it's got to buckle and make positive curvature that start to go on a sphere. Similarly, if I took like 3 octagons and stuck them together, then that's going to make a region of negative curvature. I would tile like a horse's saddle. So, starting from the honeycomb, you can introduce squares, but they're kind of regions of positive curvature. You need to cancel that with regions of negative curvature. So there's a constraint built in to maintain global flatness. And you see that the confinement is coming from the variance of the local curvature. So I put a lot of squares in, I have to put a lot of negatively curved things in as well. And when I try and make these monomer correlations, I'm summing over possible paths that they can take. They're going through lots of regions where the paths have been forced to wind around on themselves, and this is causing confinement. So there's a very natural way in which the density of squares is just measuring your variance of your local curvature. And you can quantify that precisely. So that's explaining that phase diagram, and that's our result essentially. So we haven't violated Polyakhov's theorem, and we haven't found the microscopic mechanisms of Cantor deconfinement, but we have learned a load of stuff like that. Interesting. And the take-home point is that essentially all of the things you care about in these diamond models, quantum and classical, these don't rely on periodicity. You can reformulate them without periodicity. Okay, you lose a lot of, you lose your Fourier transform, but other than that, you can do a lot of these results. Okay. So the height model requires bipartiteness, isovalence, constant valence of vertex, and a surface embedding, but that's not really a restriction because it works on any genus, but it does get harder with higher genus. These things together imply Sine-Gordon series, your classical action, as it is in the periodic cases. And in the quantum case, you can use the same arguments as in periodic cases, and you get to this compact QED. Okay, so there's long-range order. We can construct. We know that you get long-range order dimer states. Okay, I motivated the talk by saying, okay, you get periodic dimer placements, that implies confinement. Let's go to a case without periodic dimer, like there's no possibility of periodic dimer placements. What happens to confinement? The answer is, if you can write down a height model, you always have long-range ordered dimer states. And essentially, you can get those from the phase 3 colorings as you before, but it works for other cases as well. So there's always long-range dimer order, and that's the thing that causes confinement. So it's still, all of this stuff still holds. So we can construct columnar states like before, and we get these confined phases just like before. We do get an infinite temperature confinement, deconfinement phase transition tunable by geometry, which I find to be very cool, but well, that's as far as we've got. So I think I'll leave it there because I'm probably out of time. So thank you. Yes, please.
A height model requiring isovalence. You're not claiming that if you have a graph with a mixed valence versus you don't have to, because you can.
So give me an example. We have examples that do slightly weird things, but maybe you've got a better example.
So, I mean, if you have a standard example of square lattice,
yeah,
with weights, you could set one of the weights to 0.
Yeah.
And then you're going to create a possibility of having mixed valences. And if you look at the height are consistent.
Okay, so what would you be drawing? A square lattice, and then you want to delete some of the edges out of it.
Well, you want this to show them.
Okay, so I want to delete this one here. And then I want to make a height model of the same form with the diamond.
It takes a while. I've got it down here in my laptop. I could show you.
Yeah,
I won't be able to do it.
Okay.
I can show you from the screen.
I mean, our basic argument has been that even if you try and make more complicated structure, like it's vector heights or something, or generally some members of a group, like you have to add some. If I need to.
You see, you've got 3 there, 4.
Yeah, I've got 3s and 4s. So I'd say that you can't write down a height model in this case, or at least at this form.
I think you can.
Okay. Yeah, let's definitely talk about that. I'd like to.
That's means something else, right?
I think probably, but it would be good to put a restriction on what I mean by that. Yeah, okay, let's talk about it afterwards. But yeah, I'm telling you this because I'd like people to point out errors with it, because we can't come up with anything, but maybe you can.
It's not an error, but anyway.
Okay, thank you. Yes, please.
In this last case, you might have said it, I just missed it. You know, when you had the 3 colorings, and in one case you had only green squares, and in the other case the green was both squares and other shapes.
Yeah.
And so what was defined, what was defined.
Yeah.
So is there a height model description result? And if there is, what is the difference between the fields?
Yeah, okay, good question. Yeah, there is a height description. Both the difference is the relevance of that cosine term. So it's kind of known that depending on your graph structure, in fact, if you look at honeycomb versus square octagon, the argument is that the cosine term is always relevant in square octagon. That's why you get no phase transition. In the honeycomb, it's relevant at low temperatures, but there's a KT transition which becomes irrelevant. So, and that's the difference between those 2 graphs, basically. So they're always of this one of those types, and it switches over z-graphs.
Okay, so the plot kind of starts to be different.
Yeah. Any other questions? Okay. Well, I think I've basically gone over time, so maybe I should leave it there, but I'm happy to take more questions. I'm here tomorrow morning as well. Okay, thanks.
Yeah. Is there another talk now?
There is.
Do you mind leaving? Do you want to talk here? I'll have to go. Thank you. We're going to make way for the talking.
Okay.
We'll take a 5-minute break, I think. Or is it? We'll start again.
I can do that quickly.
Yeah, that's it.
Sometimes see it.
Yeah, so
How is it?
Lovely.
Yeah? You guys were in Italy,
I was visiting.
No, that's so cute.
Did you have any fun?
I don't know.
I don't know you. That's right. Okay, so
I think it's not my question. Because I think the most naive way you think is
No, but it's about getting out of the headspace. I guess. Yeah, it's about like changing the environment. I don't know. Yeah. You were just
how are you?
So,
I have a confidence. I don't know about this street. No one gives you money.
no one gives you money.
Yeah, I think probably not.
That's crazy. It's like fluids. Yeah. Yeah, no, I'll tell you the bus after. We'll talk more about it. But basically,
And the other way is thinking about it, it's kind of like, you know, if you have like
and the food was really good. I don't want to. It was actually really good. I think the treats were really nice.
because it has to be a limit when you use the.
And the Zoom is in the detail.
Yes.
Okay. Actually, really my bedroom after but it just never worked again. For me, yeah. Ever. I mean, I think the other issue was able to fix it, and then it was never really complicated.
I asked him. I was going to give you auto kicks off. And then fully have